Welcome to your Business Calculus Lesson 2.1, Introduction to Limits and Continuity. Okay, so let's define a limit. A limit is a number that the values of a function can get arbitrarily close to. And the way we read this is the limit as x approaches a of f of x equals L. So f of x approaches L as x approaches a. So let's look down here on our graph. So we have this nice parabola, or part of a parabola shown here. What translating what we have up here for our definition of limits down here, if you look as the x values get closer and closer to a, our function values are approaching this point we're calling L. And if we come from the right, okay, we pick a point for x out here just a little bit to the right of a, and we move inward, our function for the function values for the x values get closer and closer to L. So the limit as x goes to a of our function is L. Now, it appears that f of a is also L, and that's great, but f of a doesn't have to equal L. We could have a little point somewhere else. Okay, f of a doesn't even have to be defined. When we're talking about the limit, we're talking about the function values that occur as x approaches a, not the value when x is equal to a. Okay, so one way to do this is to evaluate a limit numerically. Now, if we were to try to evaluate our function when x equals 2, it's going to be undefined because we're going to get a denominator of 0. 2 squared is 4. 4 minus 2 is 2, minus another 2 is 0. So f of 2, if this is our function f, is undefined. But the limit still exists because if we look at values of x that get very, very close to 2 while being smaller, so from the left, and values that are larger than 2, that if we move from the right, get closer and closer to 2, they all approach the same value. So over here, if we plug in 1.9, we get 0.345. And if we plug in 1.99, we get 0.334. 1.999, we get 0.333. All of these values are getting closer to 1/3. As we come from the right, plug in 2.1, we get 0.322. Plug in 2.01, we get 0.332. Plug in 2.001, we get 0.33. Those are approaching 1/3 also. So the limit on the left side is equal to the limit on the right side. Our limit as x approaches 2 of x minus 2 over x squared minus x minus 2 is 1/3. We can also find limits from graphs. Now, the way that this graph is made, let me just clarify here. This is showing you that the point 0, 1 is a point on the graph. It's got a nice closed circle. The point 1, 3 is an open circle there. So there's a hole in our graph. So this function keeps going, keeps going, keeps going, and then hops over x equals 1, and then keeps going and going again. But we can still find the limit of the function as x approaches 1. So as x approaches 1 from the left, that means these points right here that are very close to 1 but not equaling 1, what happens to the function values for these x values? So we'll come up here and trace them onto the function itself. As we move there, as we approach from the left, our function values are approaching to 3. All right, so what happens if we approach from the right? If we go to values that are a little larger than 1, okay, and move in from the right. Well, if we come up here, if we move in from the right there, we're going to approach 3 also. So the limit as x approaches 1 of f of x is 3. What about for x equals 0? Well, here Let's look at what happens when we're a little bit to the left of 0. Our y value, a little to the left of 0 right here, okay? We map up onto our function. The y values are approaching 1. And a little bit to the right of 0, if we map up here and approach from the right, those are approaching 1. So the limit as x goes to 0 of f of x equals 1. Now, it's nice that f of 0 is 1, but it doesn't have to be. Just like with our limit as x approaches 1, it's still 3 even though f of 1 is undefined. We can also find limits when x goes to positive or negative infinity. And so that might be written like the limit as n approaches infinity of 1 over 10 to the nth. Consider what happens to 10 to the nth as n goes to infinity. 10 to the nth is going to get huge as n approaches infinity. I mean, even 10 to the third is 1,000. So as n approaches to infinity, 10 to the nth power is just going to be huge. Well, that's in our denominator. So 1 over a huge number gets very, very small. In fact, as n gets larger and larger, 1 over 10 to the nth gets closer and closer to 0. So the limit as n goes to infinity of 1 over 10 to the nth is 0. Okay, with 2.1, we're just going to introduce an idea of continuity. Informally, a function is continuous if it has no jumps or holes. So here we've got examples of nice, smooth functions that continue from one side of our graph to the other without having any holes or asymptotes. There's no places that the function doesn't exist. If a function is continuous, the limit as x goes to a, or as x approaches a, is equal to f of a. That's going to be something we're going to have to show moving forward. But right now, a continuous function is just one that has no jumps or holes in it. Okay, guys, thank you for listening to the lesson. Do what you can on the problem set, and then I will see you in class. Have a great day.